Thank you for coming this evening. We're going to start soon. So yeah, please get seated. Thank you.
Current spending into 2020.
Hi everybody, hello, I'm Gavin from Spartan Group. So Spartan is an blockchain advisory in Singapore, and we also have a token investment fund in Hong Kong. So today we'll be co-hosting together with BitTemple and also Tribe Accelerator. So thank you for co-hosting this event. We'll also be introducing Richard from Saito later. So I'll just pass the mic to Tata. Yeah.
Thank you everyone for coming tonight. I'm Dada from BitTemple. We are glad to have Saito and Tribe and Spartan groups tonight to come here. And BitTemple is a global blockchain hub. We provide one-stop service and also incubation service for all blockchain projects. We have hubs here in Singapore and also San Francisco, Beijing, Shenzhen, Shanghai, and also Malta and Tokyo. So warmly welcome to drop by a visit to each of our hubs, and also there are a lot of qualified projects in BitTemple. We are very glad to partner with like Huobi, Binance Labs, and also Spartan Groups and Tribe Accelerator to bring a lot of fantastic events to every members. Thank you. You can search on Telegram BitTemple to join our Telegram group. All the events we will push in the Telegram group. Thank you so much.
Without further ado, so let's invite Richard.
Thank you to Spartan, BitTemple, and Tribe for inviting us along tonight. My name is Richard Parris. I'm just going to grab the. It's behind my laptop. I'm not that coordinated, so hopefully I can manage this. I'm co-founder at a project called Saito. We're currently based in Beijing. And Saito was really born out of deep consideration of the debate that was happening through the second half of 2016 into 2017 around how to make blockchains genuinely scale, how to make very, very big data networks out of blockchains. And today I'll be giving essentially two presentations. There'll be two parts. The first one is, I think, very approachable, and we're simply talking about the motivation, the economic insights that created the motivation to create Saito, and generally about blockchains and what we see as the big impediments to blockchain scaling as data networks. The second half, I will talk about a little bit more technically, a little bit more in depth in blockchain, about our approach to solving those problems and how Saito changes the way you can think about scaling and the success we've had doing that. So getting started, this doesn't work. So today I'll be talking about economics and blockchain scaling. Yes, it's working. So what exactly is Saito? Saito is the lead character in the 2010 Christopher Nolan movie Inception. Saito was originally the code name we gave the project, and it kind of stuck, and we've never changed that. There's a little bit more to it than that. One of the key themes in Saito, and if you're the kind of person who reads project documentation or looks deeply into what we do, you'll see little Inception and Christopher Nolan references throughout. But one of the themes of the movie is looking more deeply into things to try and understand them, and that really kind of fits our project a little bit as well. So the name has stuck, and of course, every good blockchain project has an imaginary Japanese founder. Taking that theme and moving forward, let's look a little bit deeper. What is a blockchain? And a blockchain is a self-sustaining public key infrastructure network. Now, you may not hear people describe a blockchain in those terms very often, but if you look at what this means, it basically means it's a network that doesn't have any external requirements. So it keeps itself secure, it provides its own infrastructure, and it keeps running without someone paying for it or making sure that continues to happen. And the really genius insight at the heart of Bitcoin was that you can make that happen where you can't in other networks by adding money. So if you make sure that the internal, if you can find a way to turn the internal money, the token, if you can turn that into money inside the network, and use that to pay for the things the network needs, then the network essentially can pay for itself. And this was the real insight, if you think about it, with Bitcoin, where previous things like Hashcash didn't have that. They required people to have some kind of centralization. They weren't self-supporting. So Bitcoin created this space where, because the tokens had some value and you could get rewarded for doing things that the network needed with that token, the network could just support itself. There's no one running it like AWS or anything. And that's why we're all here. That works really well, and it's worked quite well for payments. But part of the dream, if you read early discussion of blockchain, was also, and particularly Bitcoin, that it would provide what we're now calling Web 3.0, an opportunity for a distributed internet with built-in security and no need for these central things like certificate authorities, DNS, etc., that could allow people to control the network. And that's really not been a lot of, it's been the focus of some projects, but we haven't really seen a lot of progress in that area because of scaling, because of the inability so far to really scale blockchains up to the size we need to do that without transactions becoming rare and expensive. That's all right. I mean, we've got thousands of technical options. We've got things like DPoS, validation, having masternodes that, you know, spread out the work in a different way. So we make an agreement that will kind of round robin the work in one form or another. We have architectural things like chains of chains or n layers of chains, graphs, which change the architecture of the chain to try and make it more flexible and able to carry more data. We have things like sharding, which are simply like, let's divide out the work. And things like avalanche, and in a slightly similar but different way, blocks, that's an interesting function, blocks and fiber, which are looking at just increasing the pace of the network underneath. So given all of the hype of last year, and given the hype of last year and all of the work we've seen on those projects, where are we? Why are we still having trouble? What could go wrong? Well, let's look at a quote from Amaury Sechet, I think one of the agreeably smarter people in the industry, in the space. He's a core developer now with, they call Bitcoin Cash again, with ABC Group. And back in October he said, when we try and solve these scaling problems, the symptoms of scaling problems, it's like playing whack-a-mole. You're hitting different problems on the head, but you can't really chase down the real problem. I like to think about it as similar to the issue you have when you're trying to put a screen protector on a mobile phone. And you're kind of pushing the bubble around, but it never quite goes in the direction you want. And I think there's an underlying reason for this. And that is that the network itself, the nodes that run the network, are simply starving for cash. If you look at POS and POW, proof of work, blockchains, this is really quite irritating. I don't know how I turn off that function. They all pay for mining. They pay for, but they don't pay for any of these other tasks. It's really irritating. I don't know why. Let's stop using that. Not interacting well with this. Okay, I'm just going to go manual from here. So if we look at the different things you need to do in a blockchain, let's think about the things we need to do. Well, there's this mining function, which is securing the network. Actually, now I'm not going point without doing any damage. There's getting the transactions from the users, propagating them around the network, putting network information around to other people to work out how to optimize the network. Now, people don't often think about that as something a blockchain needs, but you're definitely wasting time and effort if you don't. Validating the transactions, and then defending against things like double spend and other attacks on the network. Someone's going to pay for all that bandwidth that goes through the pipes for this, and someone's going to pay to store all this data. But proof of work and proof of stake really only pay for this security function. And if you ask Craig Wright, for instance, he will simply claim that the miners are paid and they won't possibly let the network collapse. And they will have a self-interested perspective, and they will go and pay for enough routing in the network to make sure it stays alive because they want to continue making money mining. Now that sounds reasonable, but it fails. And we know that it fails because we see that people don't do this. It doesn't actually work. And I think there's a reason. And yes, not a common kind of slide to see at a blockchain presentation, but I'll walk you through this. I think the reason for this is you essentially have a case of Soviet economics. It's state-run or central command economics when you do that. So let me give you two interesting stories, partially because they're interesting and partially because I think they shed a lot of light on what we're talking about here, about interesting things that happened under command economics in the Soviet Union. Toothbrushes and trains. So it was common in the Soviet Union for central, particularly in Russia mostly, for the central authorities to want to set up metrics to measure productivity in factories so that they could reward factory owners and workers for being productive. And typically you want these sort of metrics to be simple to measure. So for instance, the sort of thing that would happen is you would go to a factory, you would look at what it produces, and you could say, well, we can just count the output. Or even better, is weigh the output. So we know how many toothbrushes go in a box, we weigh the box, we get a count, we're just going to count and weigh the boxes coming out of the factory. What ended up happening, and you can go online and find pictures of giant Soviet toothbrushes, the toothbrushes just got bigger and bigger because the system was rewarding toothbrush weight. Not useful, saleable toothbrushes that people wanted, but just rewarding people for making bigger and bigger toothbrushes. So this is a great example of the problems that command economics is subject to. The train example is similar. The railway system rewarded its staff and itself on a basis of kilometre tons. How many tons have been shipped, how many kilometres? The end result was things like local managers sending a train full of lead in a circle to meet an end-of-month target, or people filling train cars with water that would leak out, but only after they'd crossed the weighbridge. So the train was measured as weighing a certain amount. And you can see again here, what you have is simply a misalignment of what you're actually measuring, right, and what the system needs. So you're not measuring value, you're measuring something else. Right? And I think this is the issue in the end with all of these command systems. If you try and give all the money to one person and then just hope that they give it out, even if they really try and do that as best possible, it's very, very difficult, if not impossible, to actually execute that in a way where the market scales. Now, an economist would say that's most likely due to a lack of price signaling. Right? Nobody's telling you what the price should be. You've just got a simple measure you're going off. So taking that back to blockchain and away from Soviet economics, a secure consensus mechanism, so the software that drives the core of the blockchain, needs to measure the work that we need to do, because we were talking before about the blockchain needs to support itself, so it's going to pay for that work that supports it. And then pay all the nodes that do the work in proportion to how much of that they've done. So it's fair. If you're putting in more work, you should get more pay for that. And prevailing theory says, and then the nodes that are getting paid, well, they can pay for everything else that needs paid, because they're getting a reward, so they'll spread that money. But we've seen, I think there's problems with that. How blockchain in the end actually ends up working. Everyone is self-interested, naturally. And they're only going to do the work that they get paid for. They're not going to do anything else they don't have to. And they will cheat or optimize, and that's often just which side of the fence you're sitting on, whether something's cheating or optimization, to get paid more than other people if they can. That's just good business. And you're going to leave everything else, as much as you're going to get away with it, to volunteers. Now the issue here is if that's what you're doing, you're capping the capacity of the blockchain at the ability of the volunteer network to support it. Right? Now those volunteers could be companies that have an interest in running a server, they could be genuine volunteers. 2013 I was running a Bitcoin node on my desktop at work. And I just kept doing that because as an open source person, when I discovered Bitcoin, it seemed like the right thing to do. But I was never going to spend a lot of money to increase the capacity of that machine, and I was going to have to take that machine and put it somewhere else if the bandwidth requirements got above what anyone noticed in the office. And so I couldn't volunteer more bandwidth than I could afford. It's not working. Sorry. And I think there's a strong argument to say you cannot prevent this. It's not just an unlucky accident. I think it's central to proof of work and proof of stake. And again, first year economics, these problems aren't new to blockchain. They're very common collective active problems that have names in economics. And the two key ones are the tragedy of the commons. Now that comes from the commons, a green space in an English village where everybody could graze their animals. And the tragedy of the commons is simply the fact that if everybody can graze their cow this year, even if that destroys the field in the future, right now I don't want to let my cow die, so I'll do it. Right? And it's very hard to collectively organize to avoid that problem. And the essence is, in blockchain context, being paid now for work people will have to do later. And in this particular case, it's that when miners put a transaction on the blockchain, on a traditional blockchain, Ethereum or Bitcoin, they're being paid now a fee. So I can take someone's money to put some data on the blockchain, and I pay a fee now. And I don't have to stick around. Now, either I don't stick around because the years pass and eventually I'm not around anymore, or because I just walk off. But at some point, somebody else will be paying to store that data on the blockchain, not me. And they've never been paid for it. It's akin to a country setting up a retirement system in a universe where people never die. Right? So each generation is just paying for another generation on top of their shoulders. Eventually that system has to collapse. So you see that creating a genuine fear of data in most blockchain projects, because they don't know how to solve that, and they're very, very scared of having too much blockchain data end up on the chain. The second problem is a free rider problem. It's very easy to understand. It's basically when some other people are doing the work and I'm getting paid for it. I'm riding for free. So I'm hanging off the side of the streetcar and everyone inside paid their fare. And the place where we see that in blockchains is exactly what we were talking about with mining. Miners are being paid and nobody else is. So they're free riding on the work that others are doing to get the transactions to them and other tasks within the network. And particularly with that free rider problem, there's a secondary problem on top of that, which I think means you can't avoid this. It's often called a Red Queen race, which comes from Alice in the Looking Glass, usually through the Looking Glass. I always get that wrong in Wonderland, but it's not. And the quote there is, obviously, miners are hell-bent in competition against each other to maintain hash power. So any miner that takes some of the money they're spending on hash power and spends it on the network is now at a slight disadvantage to any other miner who's spending all of their money simply on more hash power. And of course that advantage is going to accelerate over time. So it puts people in a case where even if they want to be altruistic, it's dangerous, but perhaps fatal, so they're not going to do it long term. So I think these problems are endemic to blockchain. To proof of work and proof of stake, there are alternatives. So now we finally get around to what is Saito. Well, Saito is an attempt to resolve these issues, to rebuild blockchain in a very similar way. It's a UTXO blockchain, the same as Bitcoin, but to do it in a way that is not susceptible to these issues. So we have a new, a different consensus mechanism, and the second presentation I'll give tonight, we're nearly over with this one, concerns itself mostly with proof of transactions and how we actually achieve this. And we do that because we really have to abandon proof of work and proof of stake. If I'm right, if Saito is right on these points, proof of work and proof of stake will always be subject to these restrictions. That doesn't mean they're useless. It just means that they won't scale in a way that isn't unrestricted that is freed from that limitation that the volunteer network will tolerate. With Saito, we try and measure value accurately. So we try and work out exactly what the blockchain is needing. And we do that through the transaction fees. That's the best measure we have, is that people actually say, I'm happy to pay this much to send this data. And then we try and work out how we can pay nodes in proportion to that without being gamed. So there's some obvious traps, difficulty. It's not so simple as to just say, oh, we'll pay everyone for the work they report, because who says they're going to be honest? So we need to make sure things like useless nodes are not going to get paid, that things like fee hoarding, if we're paying people for transaction fees, why would they share them? So how do we get rid of those selfish behaviors and make sure they're self-defeating? And as a bonus, we use some pruning and rent type techniques, and we'll talk about that soon, to make sure that the lowest paid data falls off the chain, or unpaid data falls off the chain. Now, that seems really scary to people who've been brought up or have always considered blockchain to be, by definition, a permanent ledger. And I'll talk a little bit about how that works and why that's actually a positive step. I want to be interactive tonight, so after each section I was going to quickly ask for questions, because I think it's best to get to the questions while they're fresh in people's heads. So did anybody have any questions about?
I noticed that you didn't put the Lightning Network as a solution to the scaling problem of Bitcoin.
Yep.
Is there any reason to that, or?
It's actually it's not a solution. It's actually very problematic for the network that uses Lightning. And my reasoning for that is that if you consider a world in which we lose the block reward, right? So transaction fees are the only revenue coming into the network. Lightning siphons off as much of the fees as possible. Right? Lightning is saying, don't make fee-paying transactions. Do them off-chain. Right? So it's actually going to create a place where comparative networks that have more on-chain transactions will be able to put in much more hash power and leave BTC incredibly vulnerable to 51% attacks with rented hash power. So if you have BCH or SV on the same algorithm as BTC and they're doing even 500 megabyte blocks, full of fee-paying transactions that are all paying for the hash power, and Bitcoin is doing 1 megabyte blocks with fewer transactions, and we're trying to tell people take your fees elsewhere, then you really have an issue that BTC will be remarkably insecure, if viable. And I think that's a problem that people aren't thinking about with Lightning Network. It seems like such a good idea, and I've been really supportive of the dev efforts and gone to meetups to pay for beer with Lightning and stuff. I've got the Lightning wallet on my phone, because I like tech. But the more I think about it, the more it troubles me as a kind of leech off proof of work, because it's actually taking the lifeblood of the network away. Were there any other questions?
I've seen people starting to talk a lot more about. I've seen people starting to talk a lot more about these issues in mainstream blockchains, but have you seen anyone taking steps to seriously address this in the last 4 or 5 months along a Saito model, maybe trying to take little bits and pieces of it? Do you think an existing chain with a lot of support like Ethereum could replicate something like this, or does it have to start from scratch?
Yeah, I mean, good question. So when we were raising a seed round last year, a lot of funds that were interested in tokenized bananas and then sell banana tokens really quickly and make a lot of money on bananas, or tokenized bananas. We had a lot of trouble getting people to really take these issues seriously and want to grapple with them at the level that we did. A few things have happened that are really positive, at least for us, in terms of convincing people these are important issues. We've seen a couple of 51% attacks, including the BCH, BSV, ABC split, where a lot of these issues became really, really clear to people because we really saw hash-based attacks and economic attacks in blockchain. At the same time, we've actually had a couple of really interesting things come out of the Ethereum space. The first is they're very seriously talking about rent. So they're taking seriously the idea that something must be paid periodically to keep data on chain. They're struggling with a way of working out how to pay without price signaling, without a way of actually measuring who's providing what storage efficiently. And the other thing is that Vitalik Buterin published a paper 2 months ago on what he called discouragement attacks. And we've been calling prior to that, we've been calling fee recycling attacks. And what that is in a proof of stake network, if you're prepared to stake, the assumption is you stake it for profit. But if you're a malicious attacker, you simply have to stake for break even or a slight loss. And if you are prepared to sustain that forever, you will eventually force everybody who's requiring a return on their stake off the network. And I think we are starting to see people like Vitalik think about these issues and start to consider a broader economic interplay that really comes out of the fact of that self-sustaining network needing money and economics to keep it running. So it is becoming more common to talk about these things, I think. Any other? Okay. So I think it's probably good just to move into the second presentation where I describe how Saito deals with these issues, what our attempt to solve that looks like. So let's have a look at how we try and solve these economic problems. Again, I'm going to break this into 4 discrete sections and have a quick question section after each. Just because I think it's useful to, if anyone, for people who are trying to follow along, if you do have a question, it's better to get it close to the topic. This isn't precisely technical, but it is involved, and the reason is that the blockchain, that self-sustaining structure, is pieces that rely on each other. So at the start, you can't see the logic as it fits together, and it can be a little bit of a mental exercise, but I'll try and walk you guys through that and show you as clearly as I can how we make that happen. So the first innovation, the first thing we do differently, is to have a transient blockchain, not a permanent blockchain. And we do that to solve the tragedy of the commons, to solve the problem of being paid now for work somebody else will do later. And in true Saito tradition, as I'm sure you're getting used to, we're going to start at a very fundamental thing. What is a blockchain? So obviously we all know a blockchain is a series of blocks which take as one of their inputs the hash of the previous block. And new blocks are created by taking the input of the hash of the previous block and new transactions and making a new block. And they're secured against things like 51% attacks because it becomes increasingly expensive to rewrite more of the chain because you have information, unforgeable information from the previous step at each step. So that's a standard blockchain. And somewhere back here, before this, we have our Genesis block, which was the original block, and we all know the hash of that block. This is blockchain 101. So a transient blockchain is very easy to understand. We just, at some point, start dropping the blocks. And we reset this one as our Genesis block. Now, that's heresy to a lot of blockchain people because the definition to a lot of people of a blockchain is a permanent ledger. So let me talk a little bit about this and how it's actually both safe and very advantageous in a lot of ways, particularly for a data network. Now, a lot of the concern is if it's a money network and my UTXO, my unspent, I haven't spent it yet, output is over here, it becomes increasingly expensive to rewrite more of the chain because you have information, unforgeable information from the previous step at each step. So that's a standard blockchain. And somewhere back here, before this, we have our Genesis block, which was the original block, and we all know the hash of that block. This is blockchain 101. The transient blockchain is very easy to understand. We just, at some point, start dropping the blocks. And we reset this one as our Genesis block. Now, that's heresy to a lot of blockchain people because the definition to a lot of people of a blockchain is a permanent ledger. So let me talk a little bit about this and how it's actually both safe and very advantageous in a lot of ways, particularly for a data network. Now, a lot of the concern is if it's a money network and my UTXO, my unspent, I haven't spent it yet, output is over here, and it drops off, well, I just lost my money. And yes, that would happen. And so that is something you want to deal with if you're going to use these blockchains for money, or in fact, if you're using them for data and you want that data to persist. But there's a reasonably simple solution to that. Just monitor the blockchain, and if anything important comes along, just send it. Just pay yourself. And that money will be kept on chain because now that output is spent, but it's an unspent output in this new block. So it's entirely possible to keep things on the chain. What we've changed is that I don't get the permanent storage for free. I'm going to have to pay something to keep my information on the chain. The chain is still secure so long as this chain is long enough that it's improbably expensive to rewrite back to any reasonable point. That's exactly the same as Bitcoin. I don't know anyone that I've ever met where I've asked the question at groups like this, have you ever checked that your software is correctly going back to the Genesis hash and checking all the hashes of all the blocks? No client does that. We're all basically going off the bit of the chain we've seen. And we had that issue with the Electrum SB client, I think it was, where people were getting it to look at fake nodes. And it was actually a security breach. And so that shows that people aren't really using the fact that it goes back to the Genesis block for any security. You simply need to know that you're talking to trusted nodes and that this is long enough that rewriting it's going to be stupendously expensive. And Saito actually, once you've seen the consensus mechanism, has a slightly different and very beneficial feature, which is that in Bitcoin it's basically linearly difficult, along with hashing difficulty, to rewrite the chain. In Saito it's exponentially difficult. So in a network we calculate, I think, where there's $1,000 or so US dollars worth of fees in a block, rewriting 15 to 20 blocks would cost in the order of trillions of dollars. So if you make it exponential, it becomes very easy to just wait enough blocks to get any confirmation that you need. Saito adds one feature to this, which makes it even simpler to work with. The consensus layer of the software automatically rebroadcasts transactions that meet a certain criteria. So if a transaction is either has a monetary value, an unspent output of more than a certain amount that we can fork in future to drop or raise. At the moment it's 10 Saito, which is the nominal value. But if some money is on chain and it reaches the end, it will be automatically rebroadcast. So this block will not be valid unless it contains all the transactions out of that last block that meet those criteria. The other one is that you can actually set a flag on a transaction, automatically rebroadcasting, and put in a fee to sustain that. So I could put $50 in a transaction and say, keep this on chain as long as those fees last. And that means I can pick a time and keep paying for that information to be sent round and round. So if I want to broadcast something very important, I can sign a message, put it on chain, and send it around with enough money to keep it on for a certain amount of time. The fees needed will always be determined from the average fees in the last block created. So we've now created a market price for storage on chain. We're not guessing anymore. We know precisely what the cost of storing that data should be, and it's an ongoing market cost. In fact, we can see quite simply that the total size of the chain will end up being the data appetite. That's just how much people are prepared to spend to put data on a chain, what it's worth to them, divided by the storage cost. If storage gets cheaper, then people will start putting stuff on chain and maintaining that. The nodes will maintain that at a lower price, and so more data might end up there. If people think, oh, this blockchain thing's great, I want more data on it, they will pay for more data. And we have a perpetual system here. And I would actually venture an argument that what we call the transient chain is in the long term a more secure place, especially with rebroadcasting, because it's not destined to collapse under its own weight at some point in the future. It at the very least has the possibility of maintaining the data that can afford the market price to stay on there. So that's our solution to the tragedy of the commons piece of the equation. Are there any questions on that?
Who decides what to store? Who decides what to store?
It's the market. So if anything, I mean, it's a good question. So transactions in here, so for instance, say that a transaction in here was an IoT device doing a Diffie-Hellman key exchange to secure a connection to a mobile phone. Right? Let's say that's the transaction. And that happened 2.5 years ago or 3 months ago. Nobody is going to pay to keep that on chain because nobody cares. Right? That already happened. It doesn't have a use anymore. Someone is going to have to pay for anything that wants to stay on chain. So these transactions and the rebroadcast transactions are all competing to get into blocks. Now actually the system works such that people are trying to collect fees, and I'll explain that in the next section. So people will want these fees and they'll need them to make a valid block. They'll also have access to them.
What if the user forget to pay a fee to rebroadcast a transaction?
Then it would fall off the network. Now the question is,
Let's say a user have like 1,001 transactions. Maybe some transaction is more important than the rest. But because they have too many transactions, they cannot keep track which transaction they want to rebroadcast.
A good question. I mean, I would never think that people would do that manually. Right? You would always have, it would be a feature of a wallet, piece of wallet software.
Is there like some kind of notification to inform the user that after a period of time, your transaction will fall off? So if you need to rebroadcast, at least they are notified.
So two things. One is we have this giant public database with that information right there. So any piece of software can tell you that. And then broader answer, better answer is we built a thing called Bank, which was just a piece of a Saito module that just let you send it, for instance, UTXO, and then just for that use case, not for messages, it would keep them circulating and could try and optimize the fees rather than rebroadcasting automatically. So it's very easy to write a piece of software that just says, inspect each of these blocks, or say here, for transactions from this key, and then resend them if they match this pattern.
Let's say if you have a decentralized Facebook,
Yeah.
right? So who's going to pay for the, let's say, all those comments and the pictures to be rebroadcast into the newest chain?
My argument would be nobody would do that.
Then how do you maintain all those pictures and all those comments?
Right, so it's the same as like, how is it possible that you have email from last year? The internet is not holding that email and saying whenever another server needs that email, right? You're paying someone to store it off network. If that's something you want to do, you can do it. But probably nobody wants to keep a comment on chain. You might want to make the comment on chain because it's uncensorable, because it's a public broadcast, and there's various reasons you might want to make it on chain. But what you're hoping is that people run software somewhere listening for your comment and store it if they want it. Right? So you've got to think in the mode of email. Before we just all used email as a web service and we lost visibility of this. But original POP email clients used to download off the server onto your machine. Then everyone realized that was a bad idea, let's do this in the cloud. But I think that's exactly the kind of service you'll see. So our Reddit clone does exactly that. It's actually just a server that listens to everyone's Reddit posts, we call it Reddit, distributed Reddit, and then just aggregates them. The cool thing there is it's distributed, so anyone could build a server that listen to those posts and present them in a different way, or moderate them how they like, or do whatever they want with them. So that's the decentralization there. Thanks, all.
So the Reddit that you build, this content are not being stored on chain unless you specify, saying like this particular Reddit comment I made, I want to be paid to store it on chain.
Well, in fact, there'd be little reason to. Sorry, you could rebroadcast it if you wanted to. The idea there is really that the chain is being used so that you can broadcast your comment to anybody who wants it. Right? So it's really good to think about Twitter would be a classic on-chain application because I'm just yelling to the world, I wanted to say this, and anyone who wants to listen to my key can do that, my public key. For Reddit, you're wanting to aggregate information, it's about aggregation. The reason you want decentralization there is not because people want to go trolling across the chain for the information, but because they may or may not like somebody else's decisions about what they can see, whether that's the government to a large Asian nation, or the rules at Reddit, right? People want to make their own choices about what happens to their data. It also is something we want to do because Sol might have a great idea for a new piece of software that can listen to the chain for both Twitter-type messages and Reddit-type messages, and throw in Facebook-type messages, and aggregate them in a different way for people who want that. Because the messages are going out on chain, everyone can grab them, right? Unless, of course, you encrypt them because you don't want people to. So
are these messages stored on chain,
That-
old photos, or is it just the hashed?
the whole message can go out on the chain, but the idea is that you're transmitting it, you're broadcasting it, you're not keeping it, you're not storing it on chain. So nobody would necessarily want to do that unless I might want some data to persist a certain amount of time. So the classic thing people used to have to do in newspapers, someone dies and then the lawyer can't find the family, so you have to post in the newspaper every 3 months for 2 years or something to say, please register if you want to claim this, something like that. There's certain cases we want to do something like notarize with the blockchain and keep it on chain for a while. But there's actually, when you start thinking about it, which data network cases do you want to do? What you really want is the security of the PKI network, the public key infrastructure, and the universal broadcast, and those things help you mean that you don't need centralized authorities to mitigate things.
Do you need to work with any third-party storage provider that stores all the information off-chain, and then there's certain transaction that can link to the information stored somewhere?
Yeah, so you've always got those kind of like block stack type approaches available. You can do it that way. And I think for things like content providing, so if you build a Netflixy distributed kind of thing where content providers could put their content up and aggregators could offer it, then you would do that. You would use central storage, and you'd use the blockchain to give people permission to that storage. So, split that. I think maybe one more question here, because I think we're getting a little bit into use case.
So the unspent money, is it automatically restored?
Right. If this is a choice, a design choice. It's not necessary with a transient chain to do this, but the Saito design choice was to add automatic rebroadcasting and to make sure that unspent UTXO are immediately moved back to the front of the chain. So people won't lose the financial value they have on chain.
So one of the ways I like to think about this is kind of like the Google Cloud or your average cloud storage pricing model. They're not going to ask you to pay $5 and then keep your 5 terabytes forever. They're going to ask you for a different rate every month, which they can adjust. But if Facebook, Reddit, these are examples of some software, but what is like one of the earliest pieces of like use cases for this? Like what businesses would pay a lot of money to put their data on a blockchain that they couldn't get from a permissioned network like R3 or something?
Yeah, so a great example I like, because I think it's easy for people to understand why privacy and things matter and why the features of a blockchain matter here for data transmission. Imagine that I bought an IoT camera to watch my house, maybe make sure my kids are all right when the babysitter's there, something like that, from a company in Shenzhen right, which provides, at least now they have to provide some method for the camera to connect to their data center and me to connect to their data center so that I can see that stream. And I'm just trusting them that nobody is watching that stream other than me. Now what you can do with a PKI network like Saito is you can have a QR code or an ID on the camera, and I can simply scan that with my phone. So it's very easy to build a software client that could scan that. And then my phone can send a message across the network to initiate a Diffie-Hellman key pair exchange with the phone, and enough Saito in it, enough money in it to reply to me to finish the key pair connection. We can then talk to each other quickly about where we are on the ordinary internet, not on Saito. So the phone and the camera can negotiate a path across the internet, including NAT traversal, so they can get through firewalls and things, and then establish an encrypted stream across the plain internet. So that's exactly the kind of use case you want to have, and you want to make that really cheap. That can't be Bitcoin prices to make those 6 or 7 on-chain transactions to establish everything. But then you have video streaming across the internet, which TCP is better at than any blockchain. No blockchain is going to want to do video streaming. It's going to be, it doesn't work. So it's those kind of hybrid solutions where what you're doing is end running the need to have the Shenzhen company that made the camera have any access to the video stream. And I don't need a central authority of any kind to let my phone connect securely with the camera. So those are the kind of applications we're looking to. I might cut questions there just because I want to get through things, but thanks for that. That went. I was happy with that. So now we get a little bit into the weeds, and that's because previously we were talking about solving the tragedy of the commons, and the transient chain is something that we believe just does that, and does that neatly. The solution for the free rider problem and paying the network in proportion to work done has 3 components, a little bit more complex. I'm going to go through each of those quickly, but it's a little bit abstract at first. So we introduced some concepts here. I've got a space here where I'm going to be talking about these 3 nodes. Now, right now we're at time 0 and nothing's happened and they haven't done anything. But we'll be talking about how many fees they've gathered. So the nodes on the network are all collecting transactions from users and passing them around to the other nodes on the network. And all the nodes are trying to collect fees. The reason they're trying to collect fees is to make a block, you need to have more collected fees. You have to pay this burn fee. And the only thing you can use to pay the burn fee is gathered fees from transactions. So node 1 could pay the burn fee now by creating that value of spam transactions. But it would just be donating that money to the network. There'd be no reason to do it. So let's go to t equals 1, so after say a second. And these numbers aren't really realistic, obviously they'd be bigger, but this is for explanation purposes. We can see these 3 nodes have gathered different amounts of fees. So they've just got a certain number of transactions. Probably some of them are shared. There might be the same transaction in 2 of these cases. And you can see the burn fee has also come down a bit. So what happens inside of it is, remember this is the block creation process like mining. So the burn fee goes down over time in a curve. It's actually just a 1 on X curve. It starts very, very high and goes down and eventually it's going down very slowly. The reason for that is everybody's competing to collect fees off the network. So they're piling up fees. And we want a reasonably constant block time. So we adjust this burn fee to match how long on average it takes to collect fees to be the same time, roughly. So if we go one more step, okay, we're getting closer. The burn fee is now approaching. I think we all get what's going on here. And then bang. Node 1 now has more fees than the burn fee. So it can now make a profit on whatever it has above here for making a block. So it has a small motivation now to make a block. Obviously, if it waits too long, node 2 might say, well, I'm just going to take the money and run, and node 1 is going to be left with transactions that it didn't use. And in fact, that's a real worry because if node 1 does make the block, it uses up all the transactions it has in its mempool to make that block. But these guys have some transactions that node 1's never seen. So node 1 is probably going to produce a block after these guys. And this is a really interesting property of Saito, that block production naturally disperses around the network, because people who are in a unique location with a unique source of transactions that will be able to make blocks sooner in their area. So it kind of distributes out and naturally optimizes. This is one of the ways it naturally optimizes. So that's really quick, but does anyone have any questions about that?
So your burn fee will go up and down, is it?
Yeah, so the burn fee adjusts. So basically the burn fee looks at how quickly did we collect fees enough to get above the burn fee.
That means the nodes will start off having to make a loss first because you need to pay a burn fee first?
No. So we just start and we'll wait until someone's got more transaction value than the burn fee, right? Now you'll remember when I was talking about the transient chain that I was talking about it getting exponentially more expensive to attack the network. So we can see from here, this is a good way of explaining what's going on. If I want to front run, so if I want to make blocks, if node 1 is a malicious actor, and node 1 is trying to make blocks quickly, node 1 can fill this gap with its own fake transactions, with spam. It just has to create a transaction to say, look, here's a transaction, it's valid, I signed it. And it's got this much fees in it. Now the trick is that, okay, so it makes a block, it's a valid block. And node 1's plan is to just keep doing that. No matter how many transaction fees it has, it's going to just jump in front of everybody else. Now the problem is, if the time to collect the fees to here is less than 30 seconds, because that's what we've said is the intentional block time, at least on testnet, and that's part of what testnet's testing. So block time is 30 seconds. If node 1 creates that block before 30 seconds are up, burn fee goes up. Right? So it looks at what percentage of 30 seconds it took, and it adjusts the burn fee by that. So if node 1 is constantly making blocks before everybody else, it's having to accelerate. The burn fee is going to go up and up and up and up. So while its first block may have cost X to create, the next one's X times something, and that in fact compounds. So trying to either take an old place in the chain and run faster than everybody else and get in front and invalidate all of their work, or just taking the chain wherever you want it. Both of those things are possible, but the money required, just as in Bitcoin, is too much, and the money required becomes exorbitant very quickly inside. So the key to what we're doing here is just making sure that we're taking transaction fees, the one thing we know that the network needs to slip around, and starting to measure that. We're connecting it to block production. Any other questions?
My question is about, isn't this at some point, there are two things. One is the bandwidth problem. So you're killing the bandwidth, that's one. Second thing is, at the end of the day, it depends on the scenario. You can get zero-sum game. So you are introducing like 4 kinds of fees and your golden ticket and pay split and whatnot. So to me, it's actually complicating the issue. So and you can get a lot of scams, and people can actually do an attack in between all these transactions. And how does your solution tackle this kind of intermediary thing? Because they can do an attack and they can disappear and they can go in again.
Okay, so well, 2 things there. On the bandwidth question, that's the whole point, right? The whole point is to work out how the blockchain could even possibly use up all the available bandwidth. Obviously, there's an upper limit to how much data you can put on a blockchain, but remember the intention here is to make as much data available to people as they need. So yes, we're trying to use up bandwidth, that's the exact purpose. And so part of the testing we did before launching testnet, we were seeing just how big can we go, and we put nodes in San Francisco and Singapore, and we spammed them deliberately with fake transactions, and we increased the block size, and that starts to break down with current trans-Pacific freely available DigitalOcean AWS.
How do you balance this? One go up, one go down, and up the other side go down the other side. Yeah. So where is the point of inflection? How do you calculate that? I'm very curious.
Sorry, I'm not quite following what your question actually means.
The block size versus the you know what I mean.
Yeah, okay, so I see what you're saying. I think the question is, how do we tamp down on block size? The Saito answer is, what will people pay for? Right? Someone has got to carry these blocks around the network, and so the question is, how can we put a market price on that so that it's profitable to provide hardware to do it? And that's the inflection point. It's just, if people want to use the network, how much will they pay in fees? Now, this whole thing will break down if people don't care about on-chain transactions. Right? So there's a presumption here that we're going to build software on top of Saito that makes them want to use it. Right? And I think there are lots of use cases. And the overall bandwidth used is what people will pay for. Right? If people want to add more onto the network and no one else has capacity to put more bandwidth on, then there will be people charging more and more fees for the existing transactions. The cost will go up if it's very popular. On the attacks, I think maybe we'll get to those afterwards, but I'd like to hear what the attack is you're talking about, because we've done extensive work outside.
So many.
Well, yeah. So yeah, we've done a lot of work on modeling these things out. I can't talk about them all here, so let's catch up and I'll go through what the specific ones you want to talk about, because we've actually done a lot of work on those things. But I think it's probably good to keep going here. Were there any other questions? Any other questions right now?
Two more quick questions.
Yeah, okay.
So if, let's say I'm node 3, only collect 20 transactions. Does that mean that I will need to pay more burn fee than the transaction fee that I collect? And then my second question is, at the end of the day, what is the end objective of the burn fee?
So the concept of the burn fee is just there because you need to make it difficult to create blocks. Obviously, it can't just be anyone can make a block whenever, right? Then you're just going to have fork frenzy. You need a threshold, you need a difficulty to come over. And we set that difficulty in terms of network fees because that's what we've set, the transaction fees, that's what we've set the barrier as being. If you look at Node 3's scenario, right, here's where things get interesting. So Node 1 has spent all of the transactions in its mempool, so it's now at a disadvantage to 3, right? If 3 has some transactions in here that aren't in 2, right, then even if it loses to 2 and stays ahead of 1, it's got a chance that it will be the highest next. And even if it's slower, eventually it should get somewhere. Yeah. One of the positives here is if this node here, right, never gets to the burn fee, right, because it's always only got transactions that are in these two and they're collecting more fees, it's never going to make a block. And why do we want it to make a block? We're looking at making an efficient network here. People are paying transactions. Why should we pay for a node that's just added onto the network, that's not actually achieving anything? So, I mean, in that instance, the question is, why is it trying to make a block in the first place? And what we're trying to do is create market forces that will create a network topology that actually does creates the most value.
So it's possible for node 3 to be unprofitable?
Absolutely. There's no guarantee of profitability. The idea is that we're creating an incentive for people to spot places where there might be profitability and put the hardware where it's needed. So a great example about that is if a certain organization or country or whatever blocked transactions, you could actually make money probably putting transactions on a USB stick and carrying them across a threshold of some kind and plugging them into a machine and sending them from there, because you could charge high fees. So Saito is full of incentives to make the network work. And that means if you're not profitable, if you're not doing anything useful, and we'll see more examples of that, then you shouldn't be being paid for it. You're not providing value to the network, you're making giant toothbrushes. So, or shipping carriages full of water. Okay, so we've got the good bit, payday. Someone made a block, and we were talking before about we're going to pay everybody, and what we're going to pay them is what was below the burn fee, right, the burn fee level. So the block gets to keep whatever's above that. The block producer gets to keep whatever was above that. And whatever was below that, that's what we're going to hand out. But how do we do that, right? So I'm going to walk you through some steps that we went through to work this out. We created a thing called the Golden Ticket Lottery. And that's aimed at solving this free rider. But we need to make this payment go out in proportion to the value people are providing to the network. So, again, in full Saito tradition, a network. We all know what networks look like. And here we have a single transaction. Now, obviously, all that we're talking about is, in fact, relates to thousands of transactions being put into blocks. But here we have a very simple story of a humble transaction that made its way across 3 nodes to finally be put in a block by this red node. Okay, so idea number 1. 4 nodes helped. We'll look at the transaction fee for this transaction, divide it by 4, split it up. Seems like initially a reasonable starting point. Let's think about doing that. Now there's 2 big problems with that. The first of which is if we pay per transaction, the number of payments we need to make is equal to the number of transactions in the network. So then when we make those payments, we've got to make a payment for each payment to each of the nodes, and it doesn't work. So we need to limit the number of payments we're going to make here to something reasonable. And the second is, there are going to be problems of manipulation and selfishness. So here's an obvious case. If we're just splitting the fee up between the nodes that transported the transaction through the network, if I am this node, and Andrew in the back there is that node, I might make a side deal with Andrew that I'm going to send you some transactions that you wouldn't get anyway. So he was going to get nothing before, and now, between the 2 of us, we're going to get 2/5. So long as I give Andrew something, and he gives me back more than I had when I had a quarter, we're both making money here, right? This is exactly the kind of gaming we need to prevent. How do I stop that from happening? So, what's the solution? This gets even worse, right? What stops 3 of us, so Andrew and me, from saying, look, we're going to make money out of this side of bandwidth cheating racket. We're just going to send our transactions looping. And you can think of 1,000 others onto the point of the attacks. We've modeled out hundreds of things we've thought about and we've asked other people to do to try and work out attack vectors. And the solution we've come up with is this. It's a slight linear transaction, has usable fees, and they halve with each hop in the network. By doing that, we have a very subtle thing happen. The first thing that happens is everybody after me, right, is getting less than me. So I'm happy to hand the transaction on, because without handing it on, the transaction is less likely to get into a block and I'm less likely to get paid. So we're balancing my selfishness with wanting to keep the fees for myself with my desire to actually get paid out at all by handing transactions on. And we did a lot of modeling to work out that half is actually, that was what we started with, and we went around in a big loop and got back to half is the right number for that. The other thing that happens there is, if this guy can connect to that guy, he's going to. Right? Because this guy's going to get twice the usable fees, and we'll see why that's important later. But the network's going to naturally want to bridge a gap. Similarly, if someone can put a node here that connects these 2 guys together, but these 2 guys have tiny bandwidth and they're having real trouble getting data across, if the amount of data transmitted is sufficient, then even losing half the fees will be worth it. But only if it's actually increasing bandwidth by enough that the block production is coming out that way. So we have some natural incentives now to put hardware where it should be in the network, where it's needed most and will be most profitable. And now we come to the slide that I like the least in this presentation. I tried to make things really text light and pretty to look at. This is the one that just got a bit clunky. But I think here's kind of where the magic happens as well. So you're guinea pigs here and you're seeing this for the first time. And I'll keep trying to make it nicer. But basically what we're looking at here is node 1, probably the same node we were talking about before, but could be any node, made a block with 9 transactions. And what I've done here is, of course, all the transactions end up in node 1. Some of the transactions were originated from a user connected to node 2 that got sent to node 1. Some of the transactions were originated from a user connected to node 1, so they only went through node 1, and some went 3 to 1. In this model, I've got some going 3 to 1, but no other complicated things, just because I'm trying to demonstrate what's going on here. So basically, what you notice is we count up all of these usable fees. So for this transaction, it started off at 3, 1.5, and 7.5. So that gets totaled in the block for each of the nodes in the network. And we call those, we say those fees are usable for buying tickets in our lottery, basically. So that means, given that there's 38 tickets here, node 1 has 14 38s, node 2 has 13 38s, and node 3 has 11 38s. A chance of winning the lottery, so long as the lottery is fair. Right? So this is just, it's not working out total fees. The total fees here are 26. It's just working out the relative contribution of each of these nodes to the network. So let's have a look at the story told by these transactions and see if we think it's about fair. So if we start with node 3, it didn't send anybody else's transactions along. It's probably on the edge of the network. But it did gather a full 11 Saito worth of fees. So let's just say that's our baseline, gathering 11 Saito worth of fees. Having 11 Saito worth of users input has a value of 11. Now node 2 sourced a couple of tasty large transactions from a user somewhere, and another smallish one, but it also helped transmit these two, and that comes out to about 11. So its combination of sourcing and transmitting on gives it 13 points. We could call them anything. And node 1, which only sourced 3 smallish transactions, also transmitted into the block all of the other transactions. So it gets a little payment for all of those. And that turns out to be worth 14. And that's the equation we work. Now, to make sure we're not making too many payments, all we do is we say, let's make a lottery with that many tickets, and one of them gets pulled out and someone wins. And that's how we distribute fairly. So long as you keep having these lotteries and you keep having a block every 30 seconds, this over time, like Bitcoin mining, will pay out in proportion to this measure of what is going on the network.
Where do you get the 26 Saito from?
Okay, question 1. 2 plus 2 plus 3 plus 4 plus 1 plus 4 plus 5. So it's just the original fees in the transaction, right? So this is why I don't like this. Like it's fiddly, right? This is the original fee, and then the transaction went to yeah. So nothing went from 1 to 2. Maybe one shared this transaction with 2, but that's not the transaction path that's being counted here, because we're counting the path where the transaction ended up in 1. Right? So that's why there's actually that. And of that, not all of that is the prize, because in fact we're only looking at the burn fee as a prize. A little bit of that was above the burn fee already went to node 1 for making the block. But that will tend to be much smaller than the actual block reward.
How much is the burn fee?
So it's moving, right? So we can guess here that it was less than 26, but close to 26. Because as soon as node 1 had more than the burn fee, it made the block. And it probably wasn't going to wait too long, because one of these guys would make the block. Any other questions?
So it's useful work. It's not just
Right.
hashes.
We're dropping all of the things here where a transaction went around and around or anything like that. We're only looking at the paths that actually made it. If there are any more questions, let's get to the last bit. Pay split. Now the big problem here is that I've just totally glossed over until now. How do you do a lottery in a decentralized system? We can't call in PwC or Accenture or someone to do the lottery. We can't take a trusted party. That's not what we're doing. This is a decentralized network with no central authority. The lucky thing is Bitcoin already teaches us how to do this. It has an example of how you can do this, which is hashing. So what we do is we set up a little competition, and the trick here is what we've got to remember is we're working out who gets to pull the winning ticket out. Now, if there's no competition for that, and there's no time pressure, I could just sit there looking at the tickets until I find one that takes me some time to calculate which one is the best one for me to pay me the most. But I could actually start looking at the results. So we need a time pressure to make sure that whoever pulls the ticket out has to use it. So what we do is we set up a competition similar to mining where you hash, but you're doing two things. Hashing also creates random numbers. So the first person who wins the hashing competition uses the result to pull the number. Right? And this is a way of making sure that we have fairness. And in fact, what you do is you pay people for winning the right to pull the ticket. Okay? Because if I'm being paid something for winning the right to pull the ticket, then you can balance how much money I'm going to make out of that and the risk that I'll lose it with the benefit I could get from gaming the ticket pulling. Right? So now I put my hand up and say, I've got a winner. Everyone says, okay, I pull the ticket. If I want to go and dip again, I have to come up with another win. I have to win the competition again, and someone else might beat me. So although I'm the first person to see the result, and I can look at it and see if it pays out for me, if I do that, if I take the time to look at the ticket and say, am I the winner here? Somebody else has a chance of winning, dipping and pulling out a ticket, declaring it. So we've now got a balancing mechanism without a central authority that says, how can we make sure that that lottery is fair? And it's essentially exactly the same thing as Bitcoin is doing with block creation, but the mining is nowhere near as intense. And this is where pay split comes in. Again, in Saito, we never want to say, and this is what you should be paid for that. Right? The market should always determine, we should always have price signaling determining any factor in the network. So what we simply do is we have a voting system. You could just declare pay split is 50. 50% of the benefit goes to the block producer, sorry, to the winner of the golden ticket, and 50% goes to the person who solved the golden ticket problem. The issue with that is, as the network gets very, very big, the balance of money needed for doing work in the network and the balance of money needed for making sure this lottery is fair will vary, and we should be able to adjust to that. So basically what pay split voting lets us do is balance the amount of money the network is paying for bandwidth and how much it's paying for security. So for a given range of sizes, it would probably work if you just we could hard code the pay split at a certain number. Now again, this is not something users would probably ever worry about. What would happen is that software would either ask you or be determined by its creator how it wanted to see this, and people would, in consortiums, would adjust those so that the network was maintained a level of security. Any questions on that? This is getting a little bit more obscure, so. No questions on that? No? Move to here.
Just for clarification, so you have lottery, which weighs the chances according to gathered fees.
Yep.
And then you have a hashing race, where you start going through the lottery tickets. Aren't they kind of counterproductive?
No, so
Okay.
what you're trying to do is essentially, it's like Bitcoin mining. You hash until you hit a certain difficulty, and ours is much finer grained. You're not trying to get 17 hashes at the front, with zeros at the front. You're trying to get 1 point something zeros at the front. But the idea is that you have to submit that as the winning ticket or not. Now you could take time to see if this is the winning ticket, and I've just created it. I could take a peek. Of course, this is deterministic, right? So this is why it's a problem doing something fair on a network where one person has information that the other people don't. So the only thing you can do is put us in a race, right? Because this mining is not that intensive, it's highly likely that somebody else will come up with a solution as well, pretty close to when I do. And that solution will pick someone else. So I'm just forced into a situation where I could try and game the system, right? And if there's not enough of a reward, right, for using my ticket, then it's much more in my interest to try and game the lottery. But if I get a nice healthy payment just for having found the first viable solution, then I'm going to take that money and run, and I'm going to hand it out as the lottery answer, and we're going to work out who won it. Right? So it's like Bitcoin money. It's just trying to pit two forces against each other so that you have a hope of finding a good equilibrium.
All right, thank you.
The base fee will be shared among which entity? Miners or routing?
So the pay split goes between, basically the pay split is saying once we've got this burn fee and we're going to pay that out, how much do we pay out to the routing members of the network and how much do we pay to the randomizers that are securing the lottery?
The randomizers are the miners?
Yeah, so you can call them miners, and originally we wrote the function and called it mining because it looks exactly like Bitcoin mining. But it's really important that people don't confuse it with Bitcoin mining because it's not doing the same thing.
So what's the difference between the miners and the routing node?
In the software that we run now, in the testnet prototype, it's the same node, right? So all nodes, as soon as they work out a block's been made, race off to run their miners and find a solution to the gold ticket to submit it to pick the winner. Right? So you, at some point in time, I mean, we're using SHA-256 at the moment as well. So you might, if you have big deployments of real Saito or mainnet, you might dedicate some hardware to do that.
So who will create the blocks? The routing node or the miners?
Again, at the moment they're all the same, but you could run only the parts of the software to do the relevant part. And the good thing is, again, we're not declaring how that has to work. Right? That's not kind of the Saito way. The Saito way is to say, if you work out where you put your hardware and your resources to make money, well, our job is to make sure that the incentives are always right to make that work for you and to make that fair. So there's no way of gaming it. Right? If you can do something useful, you'll get paid. Any other questions? So, we've gone through the three pieces of the solution that Saito has to the free rider problem, and I'm going to give you a quick summary and overview, a nice picture to say how that works. So basically, if you're wondering about the money flow within Saito, what you've got is transaction fees coming in from individual transactions. A slice goes off to the block creator, whatever amount of fees was in here. So imagine this is a block, all the transactions in one block. A piece goes off to the block creator that was more than the burn fee. The burn fee portion is split between Charlie. If everyone knows their Roald Dahl, Charlie is the person who wins the golden ticket lottery, and the person who created the golden ticket itself. So these are these two split the burn fee essentially. Just quickly show what pay split does. If the network votes to increase pay split, we just determine that the network is increase and the randomizers is decrease. This number can change on pay split over time. The reason that's important is if we have a very, very, very big network, we're going to want to spend a lot more money on paying for that network and proportionally less on randomization, because once something's random, it's random. It doesn't need to be more random. So bringing it all together, we initially faced two key problems, the tragedy of the commons and free riding. And we solved the tragedy of the commons by creating a marketplace for storing data on the chain through having a transient chain with rebroadcasting. Solving the free rider problem is slightly more difficult. We start off by finding a value that we care about on the network, which is gathering fees and bundling them into blocks. And we set out a way of putting that at the heart of the block creation process and the consensus mechanism. Second, we work out a way to actually pay in proportion to that work done. So we work out how to measure it, and then we work out how to pay in proportion to it in a realistic way. Right? Rather than paying for each hop, for each transaction, which is obviously impossible, we have to work out a way of spreading out the value through a smaller number of payments. And the lottery is the way we do that. Then we use pay split and randomization to make sure that that process is secure and that we're spending enough money on security to keep the network secure while also paying as much as we can for bandwidth. Right? And then everything changes when you're not afraid of data. Right? If data has a price, on your network, but that money goes to people to run the network, to provide more hardware, to buy more bandwidth, to store more data, then you stop worrying about this whack-a-mole process we were talking about in the first half. Right? Because you can simply provide more hardware to do what you need to do. And what we've seen is there's still technical enhancement we can make on our software, but we can get to multiple 100 megabyte blocks every 30 seconds, trans-Pacific, with a simple UTXO system written in JavaScript, if you're prepared to make the hardware as big as you can get. And that's the real challenge behind blockchain scaling. And what that gets us is, if we have massive amounts of on-chain data, and we solve security and scaling in one step, and we have a scenario where the more data you're routing, the more you get paid, and as much space on the blockchain as you can buy, we get the tools to build a decentralized web. We get the toolkit to make Web 3.0. You can do things like Facebook, email, Reddit, chat, games. The thing I like best is an advisor and a friend of the project at dinner in Hong Kong one night said, you know what's going to happen? Just looking at us, and he just really started getting into Saito, and he said, we're going to look at the blocks one day and they're going to be full of data that we don't know where it's coming from. And we're going to see the public keys, and the public keys is what we'll see, and we'll hunt around and we'll send messages and we'll find out someone's built something we never anticipated. There'll be something that's only possible on a decentralized internet. And that's one of the things that really excites me about Saito, is the new disruptive business models that will come out of not needing to rely on a single centralized resource to build. And remember also here, you get your data distribution for free. It needs to come from user transaction value and go to the network. But as an app developer, you don't need to pay for AWS or any deployment costs. So more people can get involved at lower prices with less threshold. Our aim is 100 terabytes of on-chain data a day. We're at 1. We do that, we're at 1 with a JavaScript deployment. We're going to start a Go rewrite reasonably soon. It's 100 terabytes a day in JavaScript, single-threaded. There are technical challenges here. One day we might use sharding to improve certain aspects of how we do stuff. But the point is, you can build that house on rock if you've solved these economic problems. If you haven't, no matter how clever your technical easing of the problems at the top level, you're still built on sand. We hope to get here within a year or two. We have a testnet up with some interesting test applications. That testnet there, so basically the network is solid and secure. The applications are still in heavy development. So we're still just trying to build demonstration products that show you can do things like send an email on chain, etc. Anyone who wants to stick around after, I'm happy to show them and walk them through getting set up. It just means all you need to do is go here. The advertising system will give you some money, and you can register an address and start talking to us on chat or using email or any of the features. They're all free and open to use. If you want to go deeper, obviously our website has information, ways of contacting us, and more of this good content. If you're a developer, you can go and look at the code base, tell us what we're doing wrong, or look at how you can build your own application. We're always interested in finding out, getting information from core developers who'd be interested in working on the project. And you can email me on the old legacy email system at richard@saito.tech, or you can come onto our testnet and send me an email at richard@saito. And again, remember to go and have a look at testnet. That's it for the evening. So thank you all for your attention. I suppose now, if there's any wind-up questions, or I'm happy to talk to people one-on-one, or let people have a look at testnet.